Welcome to iTTV for Form 5 Physics. The title of this lesson, Magnetic Effect. We've learned about magnets in our lower secondary and even to a certain extent in our primary. What we want to have a look at today is that when electricity flows through a conductor, actually a magnetic field is produced around the conducting wire. So electricity actually also has a magnetic effect. So we want to investigate the magnetic fields produced by a wire, a coil, and a solenoid, which is a coil that goes around like this. Then we want to have a look at how we could possibly make what we call an electromagnet, which is we take a piece of iron and put a coil around it, and when the current flows through the coil, the piece of iron turns into a magnet. Magnetic effect of a current-carrying conductor. Ørsted placed an electrically conductor wire near a compass, causing the needle on the compass to swerve, deflected at a right angle. He became the first to identify the force of electromagnetism. Now, if the compass needle moved, this means that there must have been a magnetic field present. The only source of the magnetic field must have been the electricity that was flowing through the conducting wire. When electricity flows through a conductor, an electromagnet is created. When electricity passes through the coils of wire, a magnetic field develops around it. A magnetic field can be represented by field lines that show the shape of the field. Lines that are closer together represent a stronger field, and lines widely spaced represent a weak field. A wire carrying electricity. An insulated wire is held vertically through a hole on a piece of cardboard. The power supply is switched on to 4-volt DC current. Iron filing is sprinkled on the top of the cardboard. The cardboard is tapped gently with a finger. The pattern of the iron filings produced is observed and sketched. The iron filings are poured away and the direction of the field is plotted using small plotting compasses. Observation. The magnetic field lines form concentric circles. The strength of the magnetic field lines is varied inversely to the distance from the wire. Compasses will show the direction of the field lines. When the current is reversed, the direction of the pointers of the plotting compass is also reversed. So when you do this experiment where you have an insulated wire going through a cardboard and you put the iron filing on the cardboard and tap it gently, what we saw was field lines being produced. Let's sketch this on the board. So we had a wire coming out where the current was flowing out of the cardboard. We'll represent this by a circle with a dot in the middle, meaning our current is coming out. Now what we saw was around the circle we had field lines. The lines were closer together near the wire, and as we got further away from the wire, the lines started to spread out, like so. What this tells us is, firstly, that the electric current is producing a magnetic field. The magnetic field is stronger closer to the wire where the lines are closer, and it gets weaker as we move further away from the source of the magnetic field. When we used the plotting compasses, we found that the direction of the field was in an anti-clockwise direction, like so. When we reversed the direction of the current, the field reversed, meaning that, I'll draw this one over here, if I had a current flowing into the paper, which I'll represent with an X, so the current is going into the paper, I got a field where the lines, once again, closer to the source was stronger, and as I went further away, the lines are getting further apart, but this time the field was flowing in a clockwise direction, like so. So when the direction of the current is reversed, the field is also reversed. So what do we understand? An electric current flowing through a conductor produces a magnetic field. The field is closer to the conducting wire, it's very strong, and as you get further from the conducting wire, the field weakens, which we can see by how close the magnetic field lines are to each other. When the direction of the current is reversed, the field is also reversed. Direction of magnetic field. The pointer of the plotting compasses show the direction of the magnetic field lines. The direction of the magnetic field can be determined using Ampere's right-hand grip rule. When the thumb points to the direction of the current, the fingers will grip around the direction of the magnetic field. So we can work out the direction of the magnetic field during examinations or tests using Ampere's right-hand grip rule. The rule is very simple. You grip the wire, imaginary wire, using your right hand, and your thumb points in the direction of conventional current, meaning your thumb must point from positive to negative. Now, let's have a look at that using these two examples. Now, in the first example, we said the current was flowing out of the board, which means that my thumb should point in this direction. Now, according to Ampere's right-hand grip rule, the fingers will grip in the direction of the magnetic field. So when my current is coming out, my fingers, as you can see, are gripping in an anti-clockwise direction from the inside of the thumb to the edge of the fingers, which is correct according to what we've drawn up here. So I point in the direction of the current and my fingers will show the field. Now over here, the current is flowing into the board, which means that it's going inwards like this. So once again, if you look at the direction of my fingers, it's going in a clockwise direction. That represents the field. So as you can see here, we have a clockwise field. So we can determine the direction in a straight conducting wire using Ampere's right-hand grip. Right-hand grip rule. Conclusion. The direction of the magnetic field can be determined using Ampere's right-hand grip rule. When the thumb points to the direction of the current, the fingers will grip around the direction of the magnetic field. Magnetic field pattern and direction due to current carrying by a loop. In the diagram, you can see a loop of wire. Now you can see the field pattern for a current carrying loop wire. Magnetic field pattern and direction due to current carrying by a loop. A simple rule to use to show the direction of current in a wire and the direction of its associated magnetic field is the right-hand grip rule. With the thumb of a clenched right hand pointing in the direction of the conventional current, then the fingers point around the current in the direction of the magnetic field. So all we're saying to you is, even if you have a loop of wire, use the right-hand grip rule. One wire will be going up, so grip around it to work out the magnetic field around it, and the next wire will be coming back down. So you have a reversed field coming back down. Once you've drawn these fields, then you'll be able to work out what the field pattern looks like. The right-hand grip rule can be used to indicate the direction of the magnetic field around a loop. Field pattern for a current-carrying solenoid. The diagram shows you a solenoid. The field pattern for a current-carrying solenoid. Now, as you can see in the diagram, the field pattern for a current-carrying solenoid looks very similar to that of a bar magnet, with a north pole and a south pole, and the field moving from north to south. Notice that the magnetic field around a solenoid is similar to that of a bar magnet. This means that there are magnetic poles at the ends of the solenoid. Magnetic field strength. Right-hand grip rule. The poles of a solenoid. If the coil is wound around a core made of soft iron, this makes the magnetic field stronger. The soft iron core will lose its magnetism as soon as the current is switched off. If the core is made of steel instead, it retains its magnetism even after the current has been switched off. So what we are saying here is that if you take a solenoid and you put a piece of iron core in the middle of it, you're going to produce an electromagnet that is even stronger than the one that we were looking at earlier. Let's sketch this on the board. So we understand what a solenoid is. A solenoid is a loop of wire that goes around like this. Like so. Inside the solenoid, as we said, we have a current. Now, as the current goes up in this direction, you can work out the field by using Ampere's right-hand grip. So, your current is moving upwards, grip according to which way the current is going, so your fingers are pointing up, which means where your thumb points will be your north pole. Here will be south. If the current is flowing downwards, then you grip like this with your fingers pointing down. Then this will be north and this will be south. As we said, we have a magnetic field that goes from north to south like so, just like we have in a bar magnet, with the lines coming in over here and going out from north here. But if I do the same thing over here, but before I make my loop, I put a piece of iron around here and I loop my wire around the iron like so. What I'm going to get is an even stronger magnet, which means that my magnetic field is going to be much stronger compared to over here. So by putting in what we call a soft iron core, I'm making an even stronger magnetic field. This word soft refers to how easily the material is magnetized. The softer the iron core, the more easily magnetized it is. If it is harder material, that means it is harder to magnetize and also harder to lose its magnetism. So therefore, something that is soft is easy to magnetize, but also easy to lose its magnetism. An electromagnet. An electromagnet, device consisting of a solenoid of insulated wire in which an iron core is placed. When the electric current passes through the coil, it induces a strong magnetic field along the iron core. So this is what we call an electromagnet, where we have a soft iron core which is placed inside a solenoid of current-carrying wire. So you need a current-carrying conductor going around your iron core that produces a very strong electromagnet. An electromagnet can be made stronger by increasing the number of turns on the coil, or increasing the current through the coil, or inserting a softer iron core into the coil. Lifting heavy cargo in the seaport. Large electromagnets are used for lifting heavy iron objects. Small ones are used in various electrical devices such as electric motors and loudspeakers. So we have a variety of uses for our electromagnet. Because we're producing a magnet that is much stronger and can be much larger, because it's actually a piece of iron with a coil around it, we can use this for a variety of purposes. They can be as small as the electromagnets in your cell phone, or they can be as large as the lifting electromagnets that we have in our seaports or in the junkyards. What are the factors that affect the strength of an electromagnet? Problem: what are the factors that affect the strength of an electromagnet? Hypothesis: the strength of an electromagnet depends on the number of turns on the coil, the magnitude of the current carried by the coil, and the use of a soft iron core. The variables: the manipulated variables, the responding variables, and the fixed variables in each case are identified in the table below. Experiment A: the manipulated is the number of turns and the responding the number of paper clips attracted. In experiment B, the magnitude of the current, the responding is the same, number of clips attracted. And in the third experiment, the manipulated is the use of a soft iron core, and the responding once again is the same. Procedure: an experiment to test hypothesis A. An iron screw is wound round with 50 turns insulated copper wire. The coil is connected to a DC 6-volt. An ammeter, a switch and a rheostat are connected in series. About 100 paper clips are placed in a petri dish. The petri dish that contains paper clips is brought near to the electromagnet, and some of the paper clips will be attracted to the electromagnet. The current and the corresponding number of paper clips are recorded in the table. We use a coil with 50 turns connected in series with a rheostat and an ammeter. I'll connect these. Connect here, and now we'll see how many paper clips we can pick up. I turn off the current. We collected 3 paper clips with 50 turns. Now I repeat using 100 turns. Connect. Disconnect. With 100 turns, we collected 3, 4, 5, 6, 7, 8 paper clips with 100 turns. For experiment B, change the voltage to 12 volts instead of 6 volts. The coil is connected to DC 12 volts as shown in the demonstration. The petri dish that contains paper clips is brought near to the electromagnet, and paper clips are attracted to the electromagnet. The current and the corresponding number of paper clips are recorded. Now we want to investigate the effect of current change on the strength of electromagnet. Once again, we have a rheostat connected in series with the electromagnet and the ammeter. We set the rheostat so that the ammeter reads 0.5 amp. We connect the electromagnet, 0.5 amps. We'll see how many paper clips we can pick up. So for 0.5 amp, we pick up 2 paper clips. Now I adjust the rheostat so that it reads 1 amp. And we repeat. Now we get 7 paper clips. Finally, for hypothesis C, place an iron screw in the solenoid. The petri dish that contained paper clips is brought near to the electromagnet and the paper clips are attracted to the electromagnet. The current and the corresponding number of paper clips are recorded. Repeat the experiment using aluminium and glass rods. So let's imagine that we have a coil like so, which is connected to our power supply. We know that this is an electromagnet. So over here we place our tray with our paper clips. So these are the paper clips. Now, to try and increase the strength of the electromagnet, we first put an iron core inside. So we place an iron core inside. So let's label that as a iron core. Now we see how many paper clips are attracted to the iron core and the coil. Once we've done this, we repeat the experiment by replacing the iron core with aluminium and then with glass. What we notice is, with the iron core, we pick up a large number of paper clips. With the aluminium and the glass, the number of paper clips picked up is significantly less. So, which factor increases the strength of the electromagnet? The factor is the iron core. Remember, iron is a magnetic material. By placing it inside the coil, we increase the strength of the electromagnet. Aluminium and glass are not magnetic, so neither one increases the strength of our electromagnet. So the electromagnet with the iron core picks up a lot of paper clips. The aluminium and the glass do not pick up a large number of paper clips. The strength of the electromagnet is increased by using a soft iron core. Conclusion: the strength of the magnetic field increases when the number of turns is increased, the magnitude of the current is increased, a soft iron core is placed into the solenoid. So the three main things that affect the intensity or strength of an electromagnet are the number of turns of the coil, the current, and using a soft or softer iron core. Please remember this because it's very common in examinations for them to ask you to modify an electromagnet, meaning that they want to make the electromagnet stronger. And in order to make the electromagnet stronger, what you need to change are the factors that we've just mentioned, which is the number of turns, the magnitude of the current, and what was the last one? Good, the use of a soft iron core. So the electric bell, this area here is your electromagnet. When I connect the circuit, and when I disconnect. Electric bell. In an electric bell, the electromagnet is switched on and off very rapidly by making and breaking contact. When the switch is switched on, current flows in the coil, creating an electromagnet. The electromagnet then attracts the hammer towards the gong to hit it. When the hammer moves towards the gong, the circuit is broken and the current stops flowing. The coil loses its magnetism and the hammer returns to its original position, completing the circuit again. In this way, the hammer hits and lifts off the gong repeatedly, making the bell ring as long as the switch is on. Telephone receiver. Changing the sound waves of the person's voice into electric currents. These variations in current strength trigger corresponding variations in an electric current in the earpiece. When the person calling speaks into the mouthpiece changes sound waves of the person's voice into electric currents. The variations in the electric currents are produced according to the speaker's voice. These variations in current strength trigger corresponding variations in an electric current in the earpiece. The receiver converts the electric current coming through the telephone line into a duplicate of the person's voice. The receiver has a thin iron diaphragm in a flexible frame surrounded by a permanent magnet. The permanent magnet exerts a constant pull on the diaphragm. Exercise. Question: what is a magnetic field? Now, remember what we were talking about earlier? What is this magnetic field? Think about it and write down the answer. Have you done it? Let's have a look at the answer. Answer: the region of space around a magnetized body or current-carrying conductor in which the resulting magnetic force can be detected. So, what is a magnetic field? It is the area around a magnetized object or current-carrying conductor in which a magnetic force is exerted. Name 3 factors that will affect the strength of an electromagnet. State how each factor will affect the electromagnet produced. We've been through these. What are the 3 factors that affect the strength of our electromagnet? Write them down. Have you done it? Good. Let's compare answers. Answer: an electromagnet can be made stronger by increasing the number of turns on the coil, or increasing the current through the coil, or inserting a soft iron core into the coil. Let's try one last question. What is the difference between electromagnet and magnet? So what is the difference between a magnet and an electromagnet? Now, what we know is a magnet is an object that has a magnetic field around it. Normally, it is ferromagnetic, meaning it's made out of iron, nickel or cobalt. But what is an electromagnet? Try to imagine the diagram of the electromagnet and write what you see. Have you done it? Let's compare answers once again. Answer: electromagnet, device consisting of a solenoid of insulated wire in which an iron core is placed. When current passes through the coil, induces a strong magnetic field along the iron core. Magnet is a piece of metal that has the power to draw iron or steel objects towards it and hold or move them. So remember, when you're describing or explaining what an electromagnet is, it is a coil of insulated wire around a soft iron core. When the current flows, the piece of iron is magnetized. Summary: electricity flows through a conductor and electromagnet is created. Please make sure you know how to draw the fields around a straight wire, a loop of wire, and a solenoid. The strength of magnetic field increases when the number of turns is increased, magnitude of the current is increased, a soft iron core is placed into the solenoid. Make sure you remember these factors because they are the common thing that they ask in examinations. That's all the time we have for this lesson. Thank you for watching iTTV.